Hello, this is our next lecture on orbital diagrams. This is pretty much a continuation of what we learned about in the last lecture with our different orbitals. These orbital diagrams are things that we draw to represent how electrons are arranged in the atomic orbitals in specific atoms. Remember, in the quantum model, each orbital holds two electrons. So, if you remember what we talked about before, each energy level 1, 2, 3, 4, n equals 1, 2, 3, 4, has a certain amount of orbitals in them so it can fit all the electrons that it needs to. And as we increase our energy level, we have more orbitals that start to appear. These orbitals have different energy levels from each other. So a 1s orbital is less energy than a 2s orbital. This here is Aufbau's diagram, and it basically shows the order of energy levels and which ones are higher than each other. So for example, 1s, and then higher is 2s, and then 2p, and then 3s, and then 3p, and then this is where it gets weird because normally you think it would be 3D, but 4S is actually lower than 3D. So when we think about elements, elements will always start to fill up their electrons at the lowest energy level orbitals. So elements would fill up 4S before they moved on to 3D because 4S has less energy than it. You guys only have to go up to 36 electrons, which is going up to 4p here. You do not need to know any of the ones after this, so it's important to memorize this order of the energy levels of, or how much energy, which orbitals have higher energy than each other. This is what the orbital diagrams look like. Each of these boxes represent a specific orbital. So the 1s is one orbital, but in 2p, we have three orbitals, which you can remember, 2px, 2py, and 2pz. You will have to remember this formatting of orbitals for the IB exam, like the 2px, 2py, 2pz. You have to remember those names. It would be the same for 3. This would be 3px, 3py, and 3pz. Again, like I mentioned, you only have to know up to the 4p. So this is what your orbital diagrams would look like. This is what a blank one would look like. So there's one more important thing to talk about before we get into how to actually make orbital diagrams, and that is electron spin. So electrons are charged negatively, right? And we know the like charges repel each other. That's a problem. Two electrons should not be able to occupy the same region of space. They should push each other away and repel against each other. Doesn't make sense. So what they found out, quantum mechanics specifically, found a solution. A pair of electrons in the same orbital actually spin in the opposite direction of each other. This makes them start to behave like magnets facing in opposite directions. And as we know, two magnets facing opposite directions, two opposing magnets attract each other. They no longer repel. So, for example, when an electron spins this way, it becomes a magnet where north is here and south is here. And when it spins this way, it becomes a magnet where south is here and north is here. And they become opposing magnets that then actually do attract each other, counteracting the fact that they were both negative in the first place. What that means is in our orbital diagrams, one box represents one orbital. Our two electrons are represented by arrows. We draw one arrow going up to be one form of electron spin, and the other arrow going down to show that it has the opposite direction of electron spin. This is just showing that we understand that electrons spin in different directions if they're in the same orbital as each other. This also is its own quantum number. We learned about the primary quantum number n, but this is the quantum number m with subscript s, which can only be 1/2 or -1/2. And that just describes for a specific electron what spin it has, either 1/2 or -1/2. So, the rules of orbital diagrams. The first is the Pauli exclusion principle. No two electrons in an atom may have the same set of quantum numbers. Each electron has different quantum numbers. What this specifically means is electrons have like electrons have like a collection of quantum numbers used to describe them, which would be like ms is 1/2 and then n is equal to 1. So that would describe a electron in the first orbital that has a specific spin, and then the other electron would be -1/2 n equals 1, just as an example. So no two electrons in an atom can have the same set of quantum numbers. The Aufbau principle, like we talked about before, an energy sublevel must be filled before moving on to the next higher sublevel. Use the Aufbau diagram, like we talked about earlier. You need to know up to 4p. And then Hund's rule, one electron is placed into each of the orbitals before a second is added. So you must spread them out horizontally if there are multiple orbitals at a given energy level before doubling up, which I will show you as we make these diagrams together. And then electrons in the same orbital must spin in opposite directions, which we draw with the up arrow and the down arrow. So let's do phosphorus together. Phosphorus has 15 electrons in it. I don't know if I wrote that down. I didn't. Phosphorus has 15 electrons in it. So what we would do is, according to Aufbau's principle, we would start at the lowest, which is the 1s, and we'd fill that up first. So we put 2 electrons, one going up and one going down. Then we move to 2s, which is the next highest, where we put 2 more in, one going up and one going down. Then we move to our 2p orbital, where we would fill up our 2px, 2pz, and 2py orbitals. And as we heard before, when we have multiple orbitals of the same energy level, you have to fill each of them, so go horizontally, before you double them up. So you would count 1, 2, 3 into each of them before you then did 4, 5, 6. So far, we have put in 10 orbitals, and there's still 5 left. So we go to the 3s energy level, and we put 2 more orbitals, one going in. And then that brings us to 12. So we know we have 3 electrons left. And like we talked about, you have to put 1 in each orbital at the same level before you would double them up. So for our last 3, they would go in 1, 2, 3 like this. And that is our finished energy level diagram. If you're confused on anything, go back and go over the rules, or of course, come up to me and ask me any questions in person. But that's the main way that we go through energy level diagrams. Let's do another example together. Here we have a bromide ion. So, bromine normally has 35 electrons. Its ion would be Br minus, and that is Br that gained 1 electron. So it would have 36 electrons in it. So we can quickly go through up to 15, because we know that 15 phosphorus looks like this, right? Where right now we have 1 in the 3p x, 3pz, and 3py orbital, but we still have 11 more. So we put 3 more in the 3p, we put 2 more in the 4s, and that brings us to 10, 12, 18, 20. We then, like we mentioned before, you have to fill each one separately, so 5 of these Ds, before you double them up. And then finally, same thing, you would put each one separately in the 4p, but we know 36, it's the most amount of electrons that you guys are allowed to have, so that actually just fills up the whole diagram. But, for example, if it was bromine, not bromine ion, so it was just bromine, it had 35, this last p, this 4py, would only have one electron in it because you'd fill each one separately, then add two more here, and then it would only be 35. And that is orbital diagrams. I really suggest you do some practice to like fully understand it. And like I mentioned, if you have any questions, feel free to ask me. But thank you so much for listening.